All right, so to follow up on the last video, I redrew a new one just to make it kind of pretty so you could see what was going on and where the interesting intersections were. Just to orient you, this orange circle here is our original circle that we drew on our horizontal horizon. Okay, and then we generated the smaller blue circle with the square, and the blue circle and the orange circle are phi related to one another. Then we took the radius of our blue circle, added to it the radius of the orange circle to get these green circles. All right, and that was to prove that because these circles are all phi related to each other, we can get a pentagon from how they intersect. So if you go to any arbitrary point, we chose the horizon lines, but you can go to any arbitrary point on the smallest circle and draw arcs through it using the radius of the original circle, and that would highlight the points. The intersections would highlight the points on that circle of where your pentagon is. But what's really interesting about this is if you extend those circles that create those arcs out completely, those circles will also intersect our original circle, and they will do so in the same spot. Okay, they will also mark out 2 of the 5 points where your pentagon will appear. And if you've already got your horizon drawn out, I've erased this one, but if you've already got it, that gives you 3 of the 5 points. At that point, you would need to either use your next size up radius in order to get the last 2 points for your original circle, or you would have to change the horizon line and turn all your circles around. So instead of just drawing the 4 that you see here, you would end up drawing, I believe it's 15. No, sorry, it's 12, because you would do it on each axis of your horizon. I might do another video to show that in action, or I might try something more complicated. We'll see. I haven't decided yet. But what's really interesting, the whole point of this wasn't to confuse you, was to actually show that if you take the larger green circles, which would be radius 3, you can see where they intersect with the radiuses of the orange circles at radius 2. Like they are hitting the exact same spot on the orange original circle, which fascinates me, the way these line up. Keep in mind that this orange circle was made with radius 2, drawn from a point on circle of radius 1. And then when you take a circle of radius 3 and draw it on a point of radius 2, they collide. They intersect at the same points on circle 2, circle of radius 2. It's a stunningly beautiful geometry, and the fact that it overlaps in such a precise way blows my mind. It's remarkable to see and to actually make it work. Now, what I'm going to attempt to do in the next one is just to show how complicated this can get. It is very easy to get lost in these architectures. If you do take what we did here, except extend it all the way around, and in fact giving you 4 pentagons inside one circle, that turns a 5-pointed star into a 20-pointed star. It's quite gorgeous, and if I can make it work in a way that makes some sense, I will be happy to share it with you. But it's a lot of lines, a lot to keep track of, and it's very, very easy to get lost in the geometry. So bear with me. I'll see if I can make that go, and I'll also bring about the other star architecture based on the tree, so we can see how that is different, and compare. Despite the fact that they don't seem to be related, I can't find a connection. They still hit the same points. So just because I can't find it doesn't mean there isn't a connection. But I'm continuing to look. But I thought it was a very pretty design and very gorgeous architecture, and the fact that it's inherent to circles, and how they relate to each other. Just like I said, it's mind blowing. All right, thanks for listening. I'll be in touch.